Welcome, everybody. Good morning. I'm really happy to see at least a couple of people, although it's quite early in the morning. My name is Mathias, and I'm going to talk about how to generate low-overhead dynamic binary translators. This is joint work with Professor Thomas Gross and the Laboratory for Software Technology at ETH Zurich. So what's it all about? Binary translation, or short BT, is a technique well known for late transformations, binary instrumentation, debugging, profiling, and to add or extend a lot of features on the fly that were not present in the original program or in the original code. But there are a couple of problems. The flexibility of dynamic software binary translation incurs at least some runtime overhead and can slow down the whole program and all that. And the complexity of all the transformations can be a challenge. So what we try is to offer a high-level interface at compile time, which will then be compiled down into effective translation tables. These translation tables are then used in a low-overhead binary translator to keep the overall translation overhead and runtime overhead as low as possible, so that we can have like a high-level interface with low overhead, enabling a lot of these late transformations and to be really flexible. After short motivation, I will give you an introduction, setting the scene, how binary translation actually work, what the different binary translation techniques are. I will discuss design and implementation of a table-based binary translator, talk about the translator techniques and all that, and the generation of these translation tables. I will then discuss some optimizations which enable a fast binary translator in a table-based optimization. And at the end, I will conclude. So what actually is binary translation? Binary translation in a nutshell is if you have like an original program on the left-hand side, you apply some transformation, and you've got an instrumental program on the right-hand side, which will then be run actually on real hardware. There is static translation for one, which analyzes the original program, checks all basic blocks, translates these basic blocks, and in the end emits an instrumented program, which will then be loaded by the loader and executed at runtime. So all the instrumentation is already present in the program when it is started, and everything is done statically. The only runtime overhead that we have is due to the added instructions or changed instructions. But we see a little cloud over there. There are some drawbacks to static optimization or static translation. What about self-modifying code? If the code reads itself and modifies itself, or if we have a JIT compiler, we will never be able to instrument these kind of programs statically because they change itself and the whole instructions and everything will not be known at translation time. On the other hand, what about dynamically loaded shared libraries? If we load these libraries, we add new code to the program which has not been translated before that. And if you go more to the malware side, what about obfuscated code? You will never be able to translate obfuscated code, or code that is, for example, available in an image or an exploit or something like that. And static translation will never be able to catch all of these cases. So we move over to dynamic translation. Dynamic translation starts the original program and gives the illusion that the original program is run. But in the end, in the back end, we instrument the program on the fly, like a JIT compiler does, and we have a just-in-time translation of basic blocks into the instrumented program. We capture all indirect control flow transfers and translate them on the fly and give the illusion as if the original program would have been run. And we translate every instruction before it is run. So whenever we see a new instruction that is about to be executed, we translate it first, catch it, and can add our instrumentation and all that. So a binary translator looks a little bit like this. We've got the original program on the left-hand side. There are a couple of basic blocks that are connected through control flow instructions. There's a small loop that we see. And then we start the program under the control of the binary translator. The binary translator uses translation tables to translate individual instructions and copy them into a code cache. The code cache then contains the translated version of different basic blocks, which are then interconnected and optimized. The table generator is an offline part that compiles down into translation tables which are used at runtime. These translation tables specify how an individual instruction is translated and what action should be taken when we encounter such an instruction. So we now have the translator that processes individual basic blocks at runtime and copies them into the code cache. If we have an outgoing edge or a couple of outgoing edges of a basic block that are not yet translated, we add trampolines. If 3' would branch to basic block number 4, we would get back into the binary translator and then add that basic block and translate it at runtime on the fly. Branch back, do a context switch into the translator, translate it, copy the translated basic block into the code cache. To keep up the illusion that the program always says that it is executed in the original location. If it reads its own machine code, it will read the machine code of the original program. It never sees code that is copied into the code cache and the code that is executed. To keep up that illusion, to fix all these, for example, return instruction pointers on the stack, or to be able to execute indirect control flow instructions, we have to keep a mapping table between locations in the original program and locations in our code cache. These two locations are translated using a mapping table that can be accessed at runtime too. So much about the basic overview. I will now discuss the prototype for a translation system like that. That's called fastBT. This is a dynamic binary translation system. The system itself is actually machine independent, operating system independent, but the focus of this talk is IA32 and Linux operating system. IA32 to be able to access and translate code of a platform that's most commonly used, and Linux because it's open source, we can access the loaders and change the whole program like that. So for an efficient binary translation, we need to be able to specify these translations and instrumentations. There are a couple of approaches which will use hard-code translation tables based on individual instructions. This is very hard for a programmer, but it's good for the binary translation system. The binary translation system uses these translation tables that describe individual instructions to translate them from the original program into the code cache. But as I already said, the manual construction of these translation tables is really hard. A programmer has to encode individual machine code instruction, has to know the whole Intel instruction manuals by hand and all that, and that's really error prone and really hard. So what we propose is automation and a high-level description. We have translation tables in the back and a table generator. We've got a high-level interface and a C++ library where you can specify high-level transformations on the machine code itself. These high-level transformations are then compiled down into translation tables, which will then be used at runtime. So we offer the high-level API at compile time to select individual changes of the machine code and compile these Intel IA32 opcode tables down into optimized translator tables, which are used of the table-based binary translator later on. What's actually possible to offer for such a compile time high-level interface? We can offer different transformations based on these opcode tables that catch memory accesses. Does this instruction access memory? What are the source, destination, or auxiliary parameters? Is it a floating point instruction, an SSE instruction, What kind of opcode is it? Is it an arithmetic opcode? Is it a lot store? What kind of immediate values are there? And so on and so on. We're able to select and specify these instrumentations at compile time and will then generate the opcodes and translation tables that are used at runtime. So that is all done at compile time. We have the high-level interface, and we're going to now move over to the runtime interface. The translator uses an iterator-based approach. Whenever we execute code that we have not yet translated, we start that iterator and iterate through every single instruction. We decode the whole instruction, also if it's like multiple bytes long, and execute a specified action for that individual instruction that is specified in the earlier translation table that has been generated. So this iterator-based approach iterates through basic blocks, copies them into the code cache, and then transfers the control back to the translator code. To achieve low overhead, we have to master several fundamentals. One of them is we have to use a code cache for translator code so that we don't have to retranslate it every time that we execute it. We have to use inlining for functions to reduce the overhead of function calls. Well, the function call itself does not incur too much overhead, but the return instruction is an indirect control flow like any other. And we have to master all other indirect control flow transfers to achieve low overhead, because these are the ones we cannot fix up. We have to do a online runtime lookup. Whenever we have an indirect control flow transfer, for example, an indirect jump, an indirect call, or a function return, we have to go through the mapping table, do a lookup, and then transfer the control to the translated location in the code cache. This is a lot of overhead, but we cannot change the jump locations in the code cache, because otherwise we would reveal the code cache and the translated code, and we don't want to do that. So to master these indirect control flow transfers, we have several optimizations. Usually we have the runtime lookup and the patching that is required. And these individual indirect control flow transfers are then replaced by a software trap, which branches into the binary translator, executes the whole lookup routine, and transfers the control back to the translator program. This is expensive. So we have several optimizations that are done in fastBT to reduce that overhead and to recover from these overheads. For one, there is local branch prediction, which predicts the location where the indirect control flow transfer will go to. There's inlining of a fast lookup into the code cache, which will check for the most common paths that we have a direct hit in the mapping table. And we can build on-the-fly shadow jump tables. And I will now discuss these optimizations in a little bit more detail. The local branch prediction that we use caches the last one or two targets in the code cache. It emits a specified code sequence which caches 2 or 1 targets that have been used before. If we have a cache hit in that target, we can redirect the control flow to the correctly translated entry in the code cache. If we have a cache miss, we look the target up in the code cache, we fix the location, and we update the cache, the local cache. This results in 3 to 5 instructions if we have a cache hit, and a couple of more instructions if we have a cache miss. This optimization works pretty good if we have a very low change rate of these indirect control flow targets and a limited set of targets. The second optimization is the fast lookup. We emit a fast inline lookup into the code cache, which checks the first location, which uses the target, does a fast hash, and looks it up in a mapping table. If it is a hit, we can directly transfer the control to the translated instruction. If it's a miss, we transfer back into the binary translator. But this optimization is more complex and costs us about 13 to 14 instructions. which is more expensive than, for example, the prediction. The next optimization that we have is a shadow jump table. A lot of the overhead that we measured, for example, in the GCC benchmarks and all that, comes from shadow jump or from jump tables. GCC tends to generate a lot of jump tables, for example, for switch statement, and initializes these jump tables. The predictor will be pretty bad, do a pretty bad job because there are a lot of targets and we have a lot of cache misses. If we now detect a jump table that is used in memory, we build a shadow jump table with translated targets. Check the translated target, branch to the translated target, and check if it's the correct one. Otherwise, we branch into a backup function. This results in a very low overhead of only 5 instructions if the target is already translated and we have a shadow jump table in place. Similar to the branch prediction, but with a whole jump table that is in the back. So the problem with all this optimization is that each optimization is only effective for some locations and a very specific program behavior. If you have a low number of changes and only few changes, if you have a low number of targets and only few changes, we use a cache. This will be pretty fast. We do the lookup the first time and can then reuse the cache all the time. If you have a high number of targets and many changes, we have to fall back to a fast lookup. That's the fastest possible to handle these cases. If the location has many different targets and the targets don't change and all are close to each other, we most presumably have a jump table. That's why I use a shadow jump table. But it's really hard to select these optimizations at compile time. If we see an indirect control flow transfer, for example, an indirect call or an indirect jump, we don't know if it's if we should use a prediction, if we should use the fast lookup, or if we should use the shadow table. So that's not known at translation time, only at runtime. And adaptive optimization, on the other hand, can select the best optimization for each individual control transfer. That's why we have an adaptive optimization that is used for all these indirect control flow transfer. We start with a prediction for 1 or 2 locations. Count the number of misses and mispredictions that we have for that optimization. If we have a specific threshold or reach a specific threshold, we recover to a fast lookup and rewrite the automatically generated code that is in the code cache. Or we construct the shadow jump table if the control transfer uses a jump table as well. So these adaptive optimizations are then able to bring competitive performance to a table-based translator. To show you some numbers, I will now discuss the setup of the benchmarks. We use null translation to show the translation overhead only. We use the spec CPU 2006 benchmarks to evaluate the performance of our binary translator. And we use the test data set to show translation overhead for short-running programs of between 2 and 40 seconds. And we used the reference data set to show translation overhead for long-running programs. This is up to a couple or up to 1,000 seconds on our machine. Related work that we compare ourselves with is HDTrans, another table-based translator where the user has to supply translation tables by hand and hard code all these translation actions. DynamoRio, an IR-based binary translator which translates machine code into an intermediate representation, does some optimizations on that intermediate representation, and translates that back into machine code. And Pin, a tool that also uses an IR-based approach to generate machine code and translate it between the different formats. So to show you the numbers for the reference data set, I selected the 4 worst performing benchmarks so that you can see the individual overheads. We compare fastBT, HDTrans, Pin, and DynamoRio. We show the overhead compared to an untranslated run. On the right-hand side, you see the overhead of the average overhead over all spec CPU benchmarks. We can see that table-based translators kind of have a problem if we compare them to Dynamo Rio. For some benchmarks, the IR-based approach is able to outperform the table-based approach in some cases. But if we check the average overhead, this is low for both table-based translators and IR-based translators. If you look specifically at the Perl bench and deal benchmark, we see that the problem of the table-based binary translators is the huge number of function calls. We have, for each of these benchmarks, we have more than 20 billion function calls that cannot be inlined in our optimizations. But nevertheless, an overhead of 50% is still pretty low for the Perl benchmark. This is an interpreter that's running another program which is then interpreted in a binary translator. So the IR-based approach will, of course, have some performance edge on that one. And we see in the analysis here that there are more than 20 billion function calls where we can still, or where we could still do a little bit better. But nevertheless, on the average overhead, if we compare these, the table-based iterators show the same performance than the IR-based ones. If we check indirect jumps, on the other hand, we see that we have the jump table optimization and the predictor. These two, both together, are able to cover about 99% or more than 99% of all the indirect control flow transfers that are there for indirect jumps. So we won't be able to do much better for indirect jumps, no matter what optimization we use. If we go to the indirect calls, we see that for Xalan and Deal, we have almost or close to 100% prediction rate where we use the prediction optimization. But for Perl bench and GOP MK, we still have the prediction doesn't work so good, and we have to fall back to the fast lookup in the end. Now, if we go to the test data set for short-running programs, on the other hand, we see that table-based iterators have a performance edge compared to IR-based iterators. These are programs that execute between between below 1 and 40 seconds. We see that most IR-based approaches are never able to recover from the translation overhead they incur. So in the end, an IR-based approach is able to keep is not able to keep the low overhead that it had for long-running programs. And table-based approach will be able to outperform these IR-based approaches. So if we compare the reference and the test data set for our binary translator, we see that for some benchmarks, for example for Perl bench, we see that the test data set is even faster than the reference data set. This is due to different instructions that are executed and a smaller set of code that is executed. So we don't incur as much runtime overhead due to the translation as if we would run the reference data set. So to summarize, we have a higher overhead if we have a lot of indirect control flow transfers. Function calls incur some overhead even with our optimizations. Indirect control flow transfers without caches or jump tables add additional overhead to these translations. Or if we have high collision rate and a suboptimal mapping table, then we have to recover to then we have to issue expensive recoveries and try different scheduling strategies. On the other hand, if we have low overhead, if we have few indirect control transfers, and the cost of the indirect control flow transfers can be reduced through the optimizations. So to conclude, fastBT, the tool that is available, shows that it is possible to combine ease of use with efficient translation. We offer a high-level interface at compile time, compile down to fast translation tables. These translation tables are then used at runtime. And at runtime, we show that we have comparable overhead to IR-based approaches for long-running benchmarks, comparable average overhead to long-running benchmarks. And we have a performance edge for short-running programs up to 40 seconds and other benchmarks. The adaptive optimizations that we've shown select the best optimizations based on an individual location, compared to earlier strategies where we had to select an optimization based on a class of control flow transfers. We now can select the best optimization based on each location of an indirect control flow transfer. And this gives us a performance edge. Adaptive optimizations that I've shown you here are necessary for low overhead in the table-based binary translators. And the table-based translator, fastBT, is available as open source. You can download it from the web page. You can use it in your projects. You can specify your transformations. And with that, I would like to thank you for your attention, and I'll be happy to answer any questions that you have.
A couple of questions. First of all, have you considered doing static jump table recovery? You can get over 99% of indirect branch targets just by static analysis of at least Spec 2006 benchmarks.
Yeah, that's actually one of the targets we would do if we were a company. The best optimization that you can have is, would be to use a combination of static translation and dynamic translation. So you can keep up the whole illusion of running the program in the original location, but you already did a lot of the static translation, have it in the back.
I mean, you could create the shadow jump table ahead of time because you know what all the targets are, and it's really easy to build all those. Second question.
But the problem is that that's actually if you would. If this would be released if there would be more people working on it, we would have already done it.
Okay.
Right. That's one thing. The other thing is the construction of the jump tables, or the cost to construct these jump tables, is really, really low. Yeah. Even at runtime. We have almost negligible runtime overhead for the translation. It's the translation itself is just a lookup in the different tables and a copy of the machine code instruction to the code cache. So this is really cheap. And if we construct a jump table, we allocate a page for that, add some specific guards, initialize that page with a lookup or like backup targets, and then when the target is executed first time, we patch it back. Mm-hmm. And this is all like very low overhead, and this won't change the big picture.
Okay. Second question. It looked like your performance numbers were really close to HD Trans and Dynamo Rio. So sell me, why am I going to pick fastBT over those guys?
It's faster than Dynamo Rio if you go to short-running benchmarks. That's for one thing.
Okay.
It's faster than HD Trans in most cases. HD Trans doesn't really offer the complete set of instructions. So it's only for a limited subset of IS32 instructions. Okay. It doesn't perform, it isn't able to execute all the SSE instructions, all the extensions and all that. And for HD Trans, you have to specify the transformations in machine code. So you specify what machine code is translated into which machine code, and you're not able to use a high-level API. So fastBT offers a pin-like API.
You have a pin-like, that's good.
With a speed of low-level implementations. So it combines the good things of both worlds. So we have like very low overhead, but you can use high-level API to select your transformations.
Okay. If there are no more questions, I've got a third. Yeah. So since you're using this table-based API, it sounds like it would be a lot easier to add a target, so x86, 64, ARM, something like that. How much work do you think it would be to implement another target?
as a translator for ARM, for example.
Right, right.
Well, you would need to specify the translation tables.
Right.
And
so how much work do you think the translation tables are?
Actually, the tables, the opcode tables are just a copy from the IA32 instruction or from the Intel instruction manuals.
Okay.
You have to just write all these tables by hand and bring them into a format that is parsable by the table generator.
Okay.
And of course, you will have to adapt the table generator a little bit to the peculiarities of the ARM CPU, for example.
All right, thanks.
Welcome.
So if you look at this in a multi-threaded environment, do you need to stop the world every time you update the code cache or do the translation? Because otherwise another thread could be running there.
Yeah,
right?
Actually that's another difference to some of the other approaches. We have thread local code caches and thread local transformations. So we differentiate between each thread and we catch pthread create and all these fork system calls that would change the layout or the number of the threads and all that. And we keep translation local. So each thread has its own thread local code cache. This enables some other speedups. So the code cache will only contain code that is local to that thread. And if we have a logger thread, we will generate code for the logger thread only. If we have a worker thread, that code cache will only contain the code for the worker methods. And this kind of forms a greedy trace extraction, where we generate traces of code that are executed on the fly. And our thread local caches will then contain these whole traces in there. This enables even some speed up in some cases. And if you look at the paper, we show that we have, for some spec benchmarks, we have up to 3.5% performance improvements, even with all the binary translation running in the background.
Just a quick question. So what's the difference between reference and test datasets? I was confused about that.
Spec CPU offers many kind of runtime flags, and you can select which ones you want to. There's the test data set, just to test your implementation, which will only run for between below 1 second and up to 40 seconds. It's like a limited, the spec CPU benchmark set consists of many different program kernels, and they have different sizes of input data sets. The test data set is a lot smaller than the reference data set. So the reference data set just runs for a longer time.
I see. And I mean, in the graphs you show actually bigger times for reference, like much bigger. Why is that actually? Yeah, actually the next one. The next slide.
Yeah.
The next slide. Yeah, in here. So I see the no BT is sorry, it was the no BT.
That's the test data set. The runtime of the test data set is a lot smaller. It's shorter to run the test programs.
This is where I got confused. So you say that test contains many more, but it's shorter in the same time. It's
the test data set, you have the same set of programs. The test data set is just a smaller input set.
So
smaller
I should
input
trust the
data.
reference more, right? Because it's bigger.
Reference runs longer.
I see, and in the graphs, you guys performing much better in the shorter one, actually, right?
Yes, because the IR-based approaches, if you run for 1,000 seconds, you have to imagine yourself there are IR-based approaches which take the machine code, translate it into a high-level intermediate representation, then do some optimizations based on that intermediate representation, and then emit machine code. These IR-based approaches will be able to recompile the code all the time if it runs for a very long time. But on the other hand, if it just runs for a small amount of time, these IR-based solutions will not be able to recover from the initial translation overhead that they had.
I see. Okay, thank you.
Welcome.
Quick question. So have you heard of Strata, and have you compared your approach? Strata, it's a binary translator from Jack Davidson and Bruce Childers and they've done a lot of work with, and the main contribution of their work is that it's extremely low overhead. So I was wondering if I think they've gotten like 4% overhead on a complete run of spec. So I was wondering if you compared your approach with Strata and...
I think the program isn't, or like the binary translator is not available openly. So I was not able to compare myself with that one.
Right. yeah, it's not, right. You kind of have to email Jack and nag him a bit, and then maybe in a few weeks you can get it. But yeah just, you know.
This translator is open source. It's GPL. You can use it in any project you want, and it's kind of easier to use and compare such projects with these closed ones. And the work he did, it was a couple of years ago, right?
Right. That was a good while ago, around the early 2000s. But cool.
Yeah. I checked his work, I read the papers, but I was not able to compare myself to him. Or reproduce his numbers, or, that's...
So what happens when the source instruction set is not the same as the target instruction set?
Then, of course, you would need to specify the translations from the source to the target instruction set. You could add, the way how it works is like we've got a huge table. For each individual instruction, we've got an action function that translates that instruction. And we have the whole IA32 specification in the background that we can use. You would then need to specify a mapping between the instructions, and then you could translate them.
So the question was, have you done that? And if you have, how do these numbers compare?
I haven't done that, but I've talked with a couple of guys about it who are interested in it. And I don't know how the numbers would look like. Currently, it's an IA32 to IA32 translator, which specifies on low translation overhead, low runtime overhead, to add profiling, instrumentation, add debugging information and all that. You can, for example, you could check all memory allocations, check the usage of different pointers, guard pages, map pages. Another option would be to like encapsulate the running program and guard it against overflows, against exploits and all that. Check system calls if they correspond to a specific parameter set and all that. But I have not done cross-platform transformation. But it's, I'm talking about it with some guys. Are there other questions? Okay, thanks again for the attention. And you're happy and free to download the binary translator, try it out, and write me if you have run into problems, and I might be able to help you. Thanks.